It's a pleasure today to welcome Pádraig MacCarron, who will be telling us about mythematics using complex networks to analyze myths, epics, and legends. The floor or the screen is yours, Pádraig.
Great, thanks very much, Evans. So thanks everyone for attending. So my name is Pádraig MacCarron. I'm a lecturer in the University of Limerick in Ireland. And I'm going to talk to you about some of my research on using complex networks to analyze mythology. So this work was done with my PhD supervisor, Ralph Kenna, who knows Colm Mulcahy, which is how Colm got in touch with me. And Ralph unfortunately passed away before Christmas. He had cancer. So I'd just like to dedicate this work to him because none of the even recent work would have been done without his idea to apply complex networks to mythology. So I'm going to start by talking about complex systems, and then I'll move into what a complex network is. So a complex system is a system where you have, there are systems that are very sensitive to small changes and small perturbations. So this is an image just of like a weather front. And you've probably heard the expression about like if a butterfly flaps its wings in the Amazon, that could cause a hurricane in Europe. And the idea is just that with a weather system, it's so sensitive to parameters and small changes that it makes it very hard to predict. And another idea behind a complex system is these ideas of emergent properties. So this is a picture of a murmuration. And you can see there's a large flock of birds. And if you study the individual constituents of a complex system, such as a bird, that will tell you nothing about these behaviors like a murmuration. So these are properties, emergent properties from these systems. So a specific type of complex system I'm interested in, I'm going to talk about, is a complex network. So in a network, we have nodes or vertices. These are just points, and they're connected by edges. So this is a snapshot of the internet. So here we've got computers connected together, which are edges. This is a picture from Mark Newman's book. And I'm going to talk a little bit now about what makes a complex network different to, say, a regular network. This is the idea of small world networks. This is the Watson-Strogatz paper from '98. This kind of set the idea of, or the whole field of complex networks going. And they show that by rewiring a regular network, you could, if you keep rewiring, increase randomness, you get a random network, but between you get this idea of a small world network. And they compared the networks of a neural network of a nematode worm, the US power grid network, and a social network of movie actors who acted in the same movie together. And they found that these three types of networks all had distinct properties from regular or random graphs, and they gave the term the complex network for those. Some of the properties they looked at were the average path length. This is the mean number of steps between any two nodes in the network. So this is Stanley Milgram here. He's the person who kind of coined the idea of 6 degrees of separation by doing this experiment with people writing letters in Boston to people in Ohio. He found that the average path length was 6. And then you might have also heard of the Kevin Bacon game, where you name an actor and you try and link them to a movie they acted with Kevin Bacon in through chains of actors. And in a complex network, the average path length is similar to that of a random graph. It tends to be quite small. It tends to be of the order of the log of the system size. Another property I looked at was the clustering coefficient, which is the number of triangles. So this is the idea that if you know two people, there's a high probability they know each other. And in a random network, this is very small. In a random network, this effectively scales with 1 over the system size, or 1 over n. Whereas in a complex network, this is often quite high, often getting values between 0.3 and 0.8, meaning that like in a social network, if I told you the clustering coefficient was 0.5, that would mean for every pair of people you know, there's a 1 in 2 chance that they know each other. So this is just an image of an Erdős-Renyi random graph, and what you do in this kind of graph is you just pick each pair and you link them with probability p. And they have the short average path lengths and low clustering coefficients, unlike complex networks with high clustering coefficients. And I'm going to just draw the degree distribution for these. I'll talk a bit about degree distributions. So the degree is the number of neighbors a node has. So if I pick this node here, for example, he's got 1 neighbor. And this random graph, I've chosen small probability p, so most of them have no neighbors. And in this case, I've generated a random graph with 1,000 people, 1,000 nodes, and I've chosen a probability of 0.05 that each pair are linked. And this will give an average degree of almost n times p. It's n minus 1 times the probability. So this gives an average degree of just under 50. So with a random arbitrary graph, if I generate, this is, I simulate this hundreds of times and just show the mean, which is the red points. If I've got 1,000 nodes and a probability of 0.05 connecting them, most people will have, most nodes in this will have a degree of 50, they'll have 50 neighbors. And then you can see this goes from, once you go less than 30 or above 70, there's almost zero probability for anyone to have anything different. Whereas if you, so this is a single instance of a random graph on the left, and this is a single instance of a complex network with the same average degree of 50 on the right. And you can see with the random graph, again, if I pick someone at random, most likely they'll have a degree close to the average. Whereas in a complex network, if I pick someone at random, most of them will have a degree much less than the average, but there's a small probability for someone to be much, much larger than what the average degree is. So the average degree tends not to tell you very much. The average number of neighbors in this, instead you need to look at the entire distribution. This is an example of 2-degree distributions. So this is, Arthur, this is a binomial distribution. And in this case, I've done lots of simulations, and you can see the green line here is a Poisson distribution. So I think in very large systems, the a normal distribution, Poisson distribution get more similar, but they are subtly different. This will decay, the standard deviation here will be smaller than in a normal distribution. And then on the right here, this one was generated using a power law. And then these two, this is a Facebook network, and this is the Enron email network. And these are log normally distributed. So in that case, it would be like taking the log of the degree, and then that would be normal. But in each case, I'm showing the complementary cumulative distribution. So that's why it goes from from 0 and it's constantly decaying. If I show the actual distribution, instead of cumulative, it would go up a little bit first and then have a very long right tail. One of the points of the degree distribution here, though, is that despite the fact that these both have fairly low average number of connections, in both cases you see people have connecting with over 1,000 people. And this is one of the features of complex networks, that they have a very long right tail, despite the fact you might have a small, or if the human's average network size is often said to be around 150, but that's not normally distributed. So some people will have have like hundreds of friends, whereas other people will have a lot less than 150. And in social networks as well, they're also found to have different properties to other types of complex networks. And one of the properties that's different about them is this idea of the assortativity. So this is the notion that the nodes with similar properties connect together. So in these networks, I'm just looking at the degree, which again is the number of neighbors. So on the left here, you can see this person with a large number of neighbors, large degree. He's connected to mostly people with small degree, and this is a disassorted network. Or here is just the Pearson correlation coefficient. And then on the right, you can see the people with the high degree are connected to people with high degree, and people with low degree are connected to people with low degree. And while this is true for degree, it's true in social networks for many other properties, such as ethnicity, age, and they all tend to be assortative. In most of these networks, however, the only information you tend to have is the degree, especially when you're going from the pure network. If you have other properties, you can use them, but often you don't have those. So we're going to use these properties to classify networks. So there was a paper in 2022 by these two Hungarian guys, Nagy and Malante, and they just took a lot of different network properties and found that these yellow ones aren't strongly correlated with other properties, and they classify networks using these properties. So I've mentioned some of these already, the assortativity. These three are from the degree distribution. This is the clustering coefficient, and this is the path length. That's just them in more detail. And what they do is they take different types of network and they use these properties and classify them. This is a t-distributed stochastic neighborhood embedding. This is similar to something like principal components analysis. It's just taking these 8 quantities here and then reducing it to 2 dimensions and plotting them. And you can see the social networks here are mostly in this region. There's some here, but then the infrastructure networks are very different, as are these cheminformatics networks. So they show that different properties of networks do tend to give rise to different types of networks. So what I'm going to do is I'm going to take a look at mythological networks. In this case, initially an interest in specific narratives, but then I'll go on to the larger myths later on in the talk. And here what we do is we'll read a myth, something like the Iliad. That's one of the examples. That's actually what the background image is here. And anytime two characters interact in the story, we record that, and then we look at the network of all of them. So I'll take about 40 different networks, and I'll compute these properties that nagging amount I do, and then I'm going to try and see what we initially hypothesized was that different cultures might give rise to different types of networks. And that was our initial guess. So let's just take a look at some specific networks. So the first three we looked at was the Beowulf, which is this Anglo-Saxon tale about this hero Beowulf. He starts off going to Geatland to defend King Hrothgar's mead halls. They're being attacked by this beast Grendel. And then later on in the story, Beowulf goes back to Denmark and he becomes king there and has to defend his kingdom from a dragon. I'm going to look at this Irish myth, the Táin Bó Cúailnge. This is the cattle raid of Cooley. Cooley is in Louth in Ireland. And this features Ireland's boy hero Cuchulainn, who is he defends the entire the people from the west of Ireland are trying to steal this magical cow, and he defends them by fighting the army in single combat night after night until the Ulster forces recover from some pangs from upsetting a goddess. They're all feeling the pains of labor by they insulted a goddess in the few generations back, and then the goddess put a curse on them that in their hour of greatest need they'd all feel the pains of childbirth and wouldn't be able to do anything. So Cuchulainn hadn't hit puberty, so he wasn't affected by the pangs, so he had to defend all of Ulster from this army. And then we look at the Iliad. This is an image of Achilles here, one of the heroes in that. The Iliad just is about the siege of Troy. It takes place just after Helen and Paris run off together. And then it tales about 2 weeks of the Trojan War, mostly while Achilles is sort of sulking because he's just miserable, really. And in the end, when Hector kills his cousin, he fights, and then it ends with the death of Hector. So this is the Iliad network here. And we've got two different types of edges. I've got a sort of gray edge for positive interaction and a red edge when two characters meet in combat. So you can see that all these characters with a lot of red edges, they tend to be the heroes. So you have characters like Achilles. Achilles is here. Hector is here. And then you've various other heroes, like Odysseus is involved in this, as is Menelaus, and they all have very high negative edges as well. And then this character here, this is Thetis, this is Achilles' mother, and at some point when Achilles is upset, she gets very upset, and all these sea nymphs come around to comfort her, basically. So that's why you get this very large clique of nodes linked together here. So that's the Iliad network. And just we take a look at the degree distribution of each of these. We see that similar to the other social networks I showed, they're strongly right-tailed. So this is the first two I talked about, the Táin and Beowulf. You can see they're very similar structures of degree distribution. On the right here, I've got the Iliad, and I've got this Icelandic saga, Laxdæla saga. This is about the settling of that region of Iceland. And you can see that in both cases, you get some very high degree characters. So this is like Achilles, Hector, Priam. They have very high degrees in the Iliad. Same with the Táin, Cuchulainn, and the two kings, Alil and Cruthur, and the Queen Maeve, all have very high degrees. And you can see there's a big jump going from like sort of seventh largest in the Táin to the largest. This is a log scale here, so this is 30, and then this is 80. And similar here, this is a regular scale. So there's a jump. You have a few characters of a degree around 60, but then you have two characters of a degree above 100. And these are just some others. This is showing that the Odyssey network is very similar to that of the Aeneid. You sort of have a very quick, fast decaying distribution initially, but then you have one or two characters that are much further to the right of everyone else. So this is Odysseus himself, and this is his son Telemachus. And in the Aeneid, this is Aeneas, who's got a much larger degree than everybody else. So they have similar shapes to their degree, and these are two Icelandic sagas as well that these are a bit more uniform, whereas these you get sort of very fast decaying and then a big jump, because these have a central protagonist. The Icelandic ones, they tend to be much more about a whole society. So while there are central characters, you don't have the same very large degree. So Egil Saga has got around 600 characters, yet the highest is a degree of 60, whereas the Odyssey has only got just over 100 characters, and the highest character has got a degree of 110. He interacts with nearly everybody in that story. So we can see already we're getting different types of network structures from these sagas. So we're going to use these 8 properties to try and classify them. And when we do this initially with these are different myths and legends we try to classify. And you can see I've colored them based on their culture. And there isn't that many, there isn't that much, there's not obvious pattern. You can see a lot of Irish stuff is around here. And then the Welsh stuff, I've colored a similar color to Irish stuff as they'd be somewhat related. The Icelandic sagas are in blue. Some of them are fairly close together. But then other ones are closer to things like Gisli Saga is closer to things like the Odyssey than it is to another saga, Njal Saga. So, as I pointed out, the Iliad is similar to these 2 sagas in some other network properties. The Odyssey and the Aeneid have very similar network properties. And they're similar to that Gisli saga that I mentioned here. So instead of coloring them by culture, what we do now is we color them by sort of the type, by genre. So I've chosen 5 genres here. Now this is a little bit subjective, I will admit. But basically these purple ones, these are all sort of set in a single location and are mostly about that region. These green ones tend to deal with like a single or maybe 2 protagonists at most, and they tend to be more centered on one character, and they will go around exploring. You get these ones of the gods, which would be like the 2 Eddas in Norse mythology. These are stories about gods and creation. And you can see these kind of cluster up here. So going by genre rather than culture, we tend to get a fairly decent classification at least. So the network properties are telling us more really about what the type of story is rather than the culture that came up with it, which isn't what when we were initially setting out this research question, we kind of thought that on culture they might cluster a little bit better. So up to now, all I've been doing is I've been looking at single narratives. We'll read through a single narrative, say Le Morte d'Arthur, and then we'll map out all the interactions with that, and then analyze that network and compare it to something else. For the rest of the talk, I'm going to talk about some recent work I've done, and some of this is very recent, so towards the end it's maybe a bit rough around the edges. In this situation, instead of taking a single text, we try and take an entire mythology. Now, we have lots of text from the Irish one, and we have lots of texts from the Icelandic one as well, but it's often quite difficult to merge them because different translators will spell names differently, so it takes a lot of work to actually merge them together. So, and then another issue is that many texts are actually missing. So we know the names of many Greek epics that we don't have, and the same in Irish. In some some manuscripts, and medieval manuscripts, they mention these Irish sagas, and some of them we have, others we don't. So what I'm interested in doing is trying to see what the effect of loss will be. So we know there are more stories than what we have. So what happens if we lose a lot of edges from our stories, if we lose a lot of interactions? How will that affect the most important characters? So like in Greek mythology, we know that Zeus, for example, is very important. But what if we only have half of Greek mythology? Will other characters be almost as important as we go on? In Greek, the answer is no, by the way. But we don't know as much about, say, Irish. There might be other characters that we're just missing a lot of tests on. So what I'm going to do is I'm going to get a dictionary of mythology, and we'll create a network from that, and we'll look at the central characters, and we'll remove some edges to see what effect that has on those central characters. So I use different data sets. I use this website, pantheon.org mythology, which is, when it started about 20 years ago, it aimed to be like a Wikipedia for mythology. So it'll have all these entries. This is just the front page for Greek mythology. If you click on Hades, it'll give you a bit of a blurb about Hades' life, and it'll name characters that he's associated with. So I take data from this for the Greek and Norse myths. I link people if they're mentioned in each other's blurbs. And then I've got a book by Peter Beresford Ellis, which is called The Dictionary of Irish Mythology, and I use that for the Irish data sets. So this is the Irish data set. So again, the edges here are directed now because if So for example, if Hades, if his entry points to Athena, for example, but Athena's entry does not point to Hades, then that will be a link from Hades to Athena, but not from Athena to Hades. So we've got the directed edges then based on whether they're co-mentioned or not. And this is the Irish ones. We've got I've named 10 characters here based on a centrality, which I'll talk about in a second. And I've colored nodes based, I've just done a clustering algorithm to try and separate them. And these are the two main cycles in Irish mythology. So they call the Ulster cycle. This is the Fenian cycle. This is the Norse myths. This is what the network looks like here. And again, I've named 10 characters. You can see Odin is here in the center, sort of overwritten others. Here's Thor. And this is one of the Valkyries. And these, again, colors here represent different communities. There's 4 communities that the algorithm found here. So what I'm interested in doing is identifying the most important characters. And I do this by using what's called the betweenness centrality. So up to now I've been talking about the degree a lot, and the degree is just the number of neighbors. But in this network here, these 3 pink nodes, they have a very high degree, so they all have, well, relative to this network, they all have a degree of 8. Where this blue node, he's only got a degree of 3, so he's not that important. But if I remove this blue node, these 3 clusters are now all disconnected. So what the betweenness centrality does is it gets the paths between every pair of vertices, shortest paths between every pair of vertices, and it gives importance to people who are on more of those shortest paths. So the characters here are named by their betweenness centrality. So looking at the top 10 characters from these dictionaries, we see that in Greek we've got Heracles and Zeus are the top 2. In Norse we've got Odin and Thor. And in Irish we've got that boy hero Cuchulainn I mentioned earlier. And this is a god associated with the sea, Manannán mac Lir. So what I'm going to do is I'm going to take these networks and I'm going to randomly remove edges to simulate loss. So if there's a story missing where, let's say, for example, Brynhild and Hel know each other and that story is lost, there will be no edge between them in the dictionary. So the process is as follows. I just randomly remove an edge, and then I get the betweenness centrality again, and I compare the top 5 sets of the top 10 instead of top 25 characters. And then I keep going this, and in each case I just remove up to 500 edges. I chose 500 fairly arbitrarily. And then I repeat this 1,000 times and get my confidence interval. Okay, so this is the Irish mythology. So the blue here is the top 5 characters, the green is top 10, and the red is top 25. And I'm using the Jacquard index, which will give a value of 1 if the sets are identical, and a value of 0 if the sets are totally different. And we can see in Irish myths there's 2,000 edges here, and by removing a quarter of these edges, the top 5 characters remain very robust. So if we were to lose up to effectively a quarter of the Irish myths that we already have, the top 5 characters won't really be affected, or at least 4 of them won't be affected. And of the character that is affected, he is still in the top 10. And even though the Jacquard index is going relatively low here by removing top 25, it's still even removing like 10% of the edges. It's around 0.7. So most of the characters are still in the top even 25. This is the Norse mythology dataset. So in this case, what you see is the top 5 is less consistent than top 10 and top 25. Again, looking at these characters, this is characters, the top 3 characters stay actually very consistent, but people like Freya and Balder becomes more important sometimes when we remove edges in particular. So there's a bit more movement around the top 5 in Norse mythology, but the top 10 is actually quite consistent. Again, there's less edges in this data set. There's about 1,500. So we're removing a third of the edges, and we find that the top 10% there still is a Jacquard index of about 0.6. So it's quite robust. The Greek one is much bigger, and unfortunately, I've only been working on this the last few days, so I haven't gone further. So I've just chose 500 edges again, which isn't particularly significant really for this many edges. But we see that in this case, the top 5 and top 10 remain almost unchanged by this.
Pádraig, we have a question in the chat that may be relevant here from Arthur O, who says, surely the experiment would be to compare the known graph of all n sagas to the known graphs of n-1 sagas, and then extrapolate forward to imagine what the graphs of n+1 sagas might look like. Would you care to comment on that? Or we
Yeah, so
could
that's
return to it
actually
later, but yeah.
Yeah, so that's actually where I'm kind of going. So as I said, I've only recently started working on this. So there are two big problems with that really. First is getting the data, right? It's very easy to get this dictionary data. What I've done is I have in PDF, and I just wrote a script to look at characters that are mentioned in it. You do have to do a bit of curation. You do have to check some characters are people and not say places, or maybe, for example, the Greek mythology. In the Greek one, nymphs were one of the most important characters, so you have to go through them to make sure they are actual characters. But that data set's quite easy to get. With these individual myth data, though, it takes a long time to get a data set, right? You have to actually read through it and get all the interactions. So we've got something like I've got around maybe 20 Irish sagas, but some of these have like 700 or 800 characters, so they take a long time to do. Others have only 30 or 40. We've got 18 Icelandic sagas, and there's about 100 Icelandic sagas in existence, and there's probably a similar number of Irish stories. So to get the full data set just takes a long time. So what my next plan is basically do what you suggest. I'll take like a subset of these Irish sagas and then see if that network looks the same, check these properties, and then do that for like take different subsets, see how consistent those network properties are, and then see if we can extrapolate those network properties forward. But that requires much more data than what I'm doing with these dictionaries. So yeah, so that's why this dictionary method is actually quite helpful, because also in a story, in a given something like the Iliad, this has almost over 2,000 edges, and the Táin also has quite a lot of interactions. Whereas when we look at the Irish, so the Irish Táin Bó Cúailnge, that has about 440 characters and around 2,000 edges. Whereas in the mythology book, this has got 900 characters. So only about 40 or 50 of the characters, basically only prominent characters, will appear in it, and only their edges will be in it. So the dictionary is sort of like a proxy for this, but it also allows us to test this edge loss much better. If we remove a lot of edges, it's much easier to remove, say, like quartered edges from this dictionary than it is to do it in all these sagas. We can just remove this given saga at a time. So what we're finding is that the Irish top five in the Irish mythology is very robust to removal, meaning that even if there were more Irish sagas to come out, the top five would be unlikely to change. In Norse mythology, the top 10 is relatively consistent. So we probably characters like Thor and Odin wouldn't be unlikely to be replaced, but some other some of the other Asia characters might be. And Greek mythology, I've got to go into this in more detail, but again, it seems like from my preliminary analysis that the main characters are very robust. So meaning that if we lost some of the data we have, they'd still be the most important. So if we were to go forward and I assume there's a lot more edges, they probably still would be more important. So just in summary, from what I've talked about, the networks of myths and epics, they tend not to cluster based on culture. Instead, their network properties tend to reflect the genre. But the central characters of these myths, they're very robust to edge loss, meaning that even if we've lost a lot of data, we haven't lost much information on the core characters, or there won't be any core gods who we don't know about. Okay, thank you very much. I'm happy to take further questions.
I actually had a question myself while I'm waiting for things to appear in the chat, Pádraig, because a few years ago, a colleague of mine wanted to know if there were mathematical techniques that could help with a little bit of sleuthing related to what you could call mythology. Namely, there are storytellers in East Africa. There's a category of storytellers who tell their stories with the aid of a device called a Lukasa board, which appears to have, or at least one can imagine easily, that it has a network structure. But this art is dying off, and my colleague was wondering if there were mathematical methods that might be able to help reconstruct what the information is in these boards. It's known that the people use these boards to narrate things about the histories of their clans and relationships among people and perhaps historical things of the larger community. I wonder if you think there could be some potential there for the methods that you're talking about to obviously you can't reconstruct a myth that's lost, but could one perhaps get a good estimate of the number of characters or the number of themes in such a situation?
Well, definitely for this kind of work, something like the number of characters, information on characters, and again, character importance could be retained. Um, for the full story and for these
No, the
boards,
full story, no, but something about it.
yeah, well, I mean, I think this method does work quite well. Like if you look at the top characters here, so nobody's going to argue really that there's more important characters in some of these myths than what this dictionary method is finding, right? And this is basically, okay, maybe the order is a little bit arbitrary, but in Norse in particular, and in Irish, these top five are by far the most important characters. Actually, these two are a little bit suspicious. There's you might have noticed in this network there is these kind of disconnected edges. So they're showing up highly on that because of this. But the top few characters are they're robust to loss, but also the network is able to identify those. So it might be a good way to sort of a simplistic way, but a good way to just sort of keep their main characters and keep knowledge of them.
Yeah.
If that would be something of use to them. In terms of, you mentioned something else there as well, other than characters, maybe the themes. There would be sort of, there are like some kind of narrative, there's working narrative networks that I think look at themes or try to identify themes from stories. Maybe not so much from a network approach, really more a natural language processing approach. Um, so I think you could, there might be something that you could do there, but that wouldn't really be my area.
Yeah. We have some questions in the chat
Yeah.
appearing now. So Peter Rowlett says, the cultures you mentioned are fairly interconnected in the sense of being influenced by each other. Might there be differences with more different cultures?
Yeah, that is a good question, and this is one of the sort of disadvantages really that a lot of the work we have looked at is very European centric. You might notice though that there is this Indian one, the Mahabharata, and there's also the Popol Vuh somewhere, which is this South American story. So you wouldn't expect any major influence on them. Um, Having said that, also I guess I should have pointed out that some of these stories, while the cultures might have influenced, there can be massive time periods between when the stories were recorded or even told. Like the Irish stories, these were all recorded around sort of roughly around the 12th to 14th century. And despite the fact that some of these they involve some of the older godlike characters, they're very Christianized. There's a lot of influence of Christianity on those stories, whereas that won't be the case in, say, maybe some Greek or Norse stuff, or to a lesser extent. So what we have often is influenced by Christianity as well, which might affect us. But yeah, there's nothing stop you getting other cultures beyond what we've done. Partly, like I started the Irish stuff because I'm kind of more interested in this. And yeah, I've added other things. I've added Lord of the Rings, for example, and we have done a network analysis of Game of Thrones too. I didn't include that in this particular one, but there's nothing to stop you from choosing other cultures. I would like to do more on some Eastern stuff, and those actually that Pantheon.org that has data on Philippines and Maori myths, which I would like to include. I have the data for them, but I kind of briefly mentioned earlier the hard part is going through and making sure all the characters are actually characters and not, say, collections of things or places. So it does require reading through each entry or scanning through them at least. So that's why I haven't included those yet, but I would like to include those other cultures and see if there's much difference and if this method will work much further beyond European stuff.
We then have a remark from Arthur O. Odysseus seems crazy high at number 5. Is that only the influence of the number of minor characters in the Iliad and Odyssey, he says, and then in a separate line says Lord of the Rings is also in there.
I would imagine this is account of Odysseus being the central character of the Odyssey, and then also fairly prominent in the Iliad. Um, I haven't really gone through the entries in detail to see. Well, you also have to remember that this is taking the betweenness, right? So,
Yeah.
because he's quite central in two stories, his in betweenness might be inflated. If I took something like maybe there's his number of connections. I think some more of the gods would probably feature a little bit more. Um, but think any character who is sort of like so Priam is also very high, right? So Priam is the king in Troy, and I think any relatively central character in the longer epics might dominate a bit more than they should, simply because a lot of the stories tend to be much shorter and feature less characters. But no, I do need to look into this a little bit more. I should just take a look at this use entry and see is it maybe even. So I haven't gotten through the data enough to see if it's how well it might be much more fleshed out for Odysseus than someone like Hermes, for example.
Yeah.
So there's obvious disadvantages with using this dictionary method, but as I say, it's a very fast way to get seemingly fairly reasonable data.
I'm sure I speak for everyone by saying that was a fascinating talk.
Thanks very much, and thanks for all the questions. Great to have questions coming in during it as well. Makes it a bit more maybe more engaging for me.